Your favorite drummer, toddler, grandmother, and scientist. What do they have in common? You guessed it, they all know how to count. Numbers and patterns, this time on Science Without Walls. Scientists report data and observations so that their experiments can be understood and reproduced by others. Science is based on the reproducibility of experiments in different laboratories at different times, meaning that the recorded observations have to be objective, precise, and quantitative. So that, of course, means that scientists had to learn to count. We'll deal with 6 key topics in this program: powers of 10, units, basic quantities, significant figures, decimals, and estimation. First, powers of 10. Cosmologists may count in units of billions of years in time and light years in distance. Geologists count in units of millions of years of time and kilometers in distance, like going to the bottom of the Grand Canyon, 15 kilometers down and 2 billion years into the past. You and I tend to worry about minutes, days, the next midterm, or the final. We all count, whether we are counting pennies or dollars, watching the speedometer on our car, or the pieces of pizza left for our hungry group. We know how to count, add, subtract, multiply, and divide. We call all that arithmetic.
How about a 3 and a 6 and an 8 and a 2? I'm going to add those up.
Arithmetic is a part of mathematics, the language of numbers and patterns, of order and relationships. For many, mathematics is a subject and a passion in its own right. It includes logic and statistics, geometry, algebra, and calculus. The University of Utah teaches over 100 different mathematics and statistics courses. For scientists and engineers, musicians and architects, mathematics is a tool to help them discover relationships and patterns, order in the world, a tool to help them visualize and simulate, model what might be going on. We can't do science without at least some mathematics. Galileo said, "The great book of nature can be read only by those who know the language in which it was written, and this language is mathematics." So hang on. In this program, we're going to take a quick ride through parts of the world of mathematics. Everyone likes to count.
5, 6, 7, 8.
Particularly if they are counting something desirable or valuable. Like the poorly paid little scientists on the screen, we'll count. You know the value, the size, the weight of a penny. You know its color and its shape. Fortunately, money or currency is counted around the world in powers of 10. 1 penny, 1 dime, $1, $10, 100, 10 hundreds, or 1,000. Sorry, we can't directly show you more than $1,000. Most of us have 10 fingers and 10 toes. When you first learn to count, they are very helpful tools. Maybe they still are. The abacus is a great calculating device, which essentially provides a way to count with your fingers that's faster than counting on your fingers. It's been around for thousands of years. The abacus was developed for economic and financial applications. Later came slide rules, calculating machines, and the modern electronic calculator, and computers. Here are 100 pennies and a dollar bill. And here's $100 and a $100 bill. $100 is 100 pennies times $100. That's 10,000 pennies, a big and heavy pile, impractical to carry around. If you want to buy something for $100, you certainly don't want to have to pay for it with 10,000 pennies. So we have ways of expressing numbers, of expressing value in various quantities or units. 1, 10, 100, 1,000. Powers of 10. Since scientists often deal with wide ranges of numbers, they use scientific notation, which is just an easy way to express powers of 10. Let's use the penny as our basic unit. 10 pennies to a dime, 10 dimes to a dollar, that's 100 pennies. 100 pennies in a dollar, 100 is 10 times 10, or 10 squared. $10 is 10 times 100 pennies. Well, 10 times 10 squared is 10 cubed. See, we're now playing with exponents. 10 squared equals 10 times 10, that's 100. 10 cubed equals 10 times 10 times 10, that's 1,000. This elevated guy here is called an exponent. Here are some more general examples. A cubed is A times A times A. A to the fourth power is A squared times A squared. If A happens to equal 10, then A cubed is 1,000. You get the idea. $1,000 is 10 cubed dollars. How many pennies? $1,000 times 100 pennies for each dollar. That's 10 to the fifth cents. That's 100,000 pennies. Dollars and cents are units. I was asking how many pennies, so I converted the dollars to cents. And we just did a conversion of units. We converted from dollars to cents. Scientific notation in powers of 10 lets us deal with really big and really small numbers. A million is 10 to the sixth power. You and I don't normally have to work with numbers that big or bigger, at least in terms of money. The state auditor does. Utah's state budget is several billion dollars a year. That's 10 to the ninth dollars, or 10 to the 11th pennies. Of course, if that auditor should become treasurer of the United States, then she has to start worrying about a $1 trillion budget, or more than $1 trillion. A trillion is 10 to the 12th, $1,000 billion. It's $1 million. Scientists and economists use powers of 10, or scientific notation, because they can cover an enormous range of numbers with a very simple way of writing. A lot of people don't worry about pennies anymore. Most checkout counters have this little cup, so you don't have to worry about pennies either. You can put your extra ones there and take a few if you need them. A penny has become almost insignificant. A nickel is still significant, and dollars are certainly significant. On your friendly federal and state income tax returns, you don't need to worry about pennies. You can do everything to the nearest dollar. Pennies don't have much significance to you or to the Internal Revenue Service. That's good news. Money, currency, is primarily in powers of 10, whether you're in Australia, Portugal, or Canada. What about length or distance? Well, that's bad news in the United States. We measure distance in feet, in shoe sizes. This is 1 inch, the length of a finger joint, and there are 12 of them in a foot. If you're 6 feet tall, how many inches? Well, multiplying by 12s is a lot tougher than multiplying by 10s. You had to memorize your multiplication tables so you could quickly answer problems like 6 times 12. Yes, that's 72. Oh yes, and there are 8/8 in an inch. And don't forget the 3 feet in a yard. That's the distance from some queen's nose to her extended thumb, I think, or 36 inches. Nobody likes to deal with such cumbersome numbers. That's part of the reason why much of our nation is somewhat innumerate. Most people don't like to do arithmetic because the arithmetic can be pretty cumbersome, unless we're dealing with money where everything is in powers of 10. That's why this little book, Innumeracy, by John Allen Paulos, is so important. Please read it, especially if you're innumerate. It's enjoyable, refreshing, and very well written. In Europe, and in most of the rest of the world, they don't measure distances in inches, feet, yards, or miles. They measure them in meters, a bit more than a yard. And they don't have to deal with 1/12ths of a meter. They only care about powers of 10. 1/100th of a meter, a centimeter, a little less than half an inch. 1,000 meters is a kilometer, a little more than half a mile. 1,000th of a meter is a millimeter. In the metric system, it's really easy to go from millimeters to centimeters to meters to kilometers. And in our system, it's really tough to go from miles to yards to feet to inches. So since scientists are basically simple folk, they like to deal with numbers in as easy a way as possible. They always work in the metric system, and so will we. If you aren't already used to it, just get used to it. It's so much easier than working with feet, pounds, pints, and tablespoons. The reason you're so familiar with the English system of units is because that's the way you were brought up. Your brain is already hardwired to appreciate those dimensions and quantities. But you're still young. A few good neural connections, and you'll be thinking in the metric system. Even good old England, from which we inherited the cumbersome English system, is now going metric, although the old-timers there are complaining and moaning. You're generally familiar with rulers, yardsticks, and tape measures. Most modern ones are labeled in both inches and centimeters. So use a cloth tape measure, labeled in millimeters, centimeters, and meters, as well as in inches and feet. I'm almost 6 feet, 72 inches, 183 centimeters, 1.83 meters tall. How about your height in centimeters and meters? My waist, I'm sad to say, has grown to about 33 inches. But if I were ordering clothes or pants in Europe, I, of course, would have to say 84 centimeters. So please run around your house or apartment, measuring everything in sight. Get a feeling for centimeters and meters versus feet and inches. The world uses the metric system. The only major exception is the good old USA. We have insisted that the rest of the world translate their easy, rational system into our cumbersome, complex, and out-of-date system. It just doesn't make any sense. It's time we adopted a system that is far more rational and easier to use. Although mathematicians can be fascinated in numbers by themselves, the rest of us generally use numbers to represent certain things. You may be interested in 2 books and 3 oranges. If I asked you to add 2 books and 3 oranges and give me a number, you'd shake your head and worry a bit about my sanity. I could ask you to add 4 oranges and 2 oranges, and you would give me 6 oranges. But adding 2 oranges, 2 staplers, and 2 books is a senseless problem. So we have to deal with units as well as numbers, whether those units are oranges, books, or staplers, or centimeters, or feet. In some cases, you can convert the units. Let's add 2 inches, 10 centimeters, and a meter. Those 3 quantities deal with distance, so it makes sense to add them. So like units can be added, even if they are expressed in different ways, different units. I just have to be able to convert the units to a common unit. For example, you can add units of time, even if they are expressed in hours, days, and minutes. The really basic units in science are distance, that's length, generally given in meters, mass, generally given in kilograms, time, and temperature, given in Celsius degrees. Everything we do in science uses these 4 basic units. Later, we'll add a couple more to the list. How far do you live from the University of Utah? Well, if you're 10 kilometers from the university, you'd probably give me an answer to the nearest kilometer. You wouldn't give it to me in meters, and you certainly wouldn't give it to me in millimeters. You might give it to me in miles or in half miles, but you wouldn't give it to me in feet or inches. So we tend to deal only with numbers that have significance. Let's add a kilometer, 100 centimeters, and 11 millimeters. These are all metric measures of distance, so we can certainly add them up, but they are in different units. So first, let's convert them all to a common unit. The smallest unit is the millimeter, so we could convert them all to millimeters. How many millimeters in a kilometer? Well, there are 1,000 meters in a kilometer, and there are 1,000 millimeters in a meter. So 1,000 times 1,000 is 1,000,000, or 10 to the 6th. Let's write it as 1,000,000. Now to the 100 centimeters. Since there are 10 millimeters in a centimeter, that's 1,000 millimeters. And our final number is 11 millimeters. So how do you add up 1,000,000 millimeters, 1,000 of them, and 11 of them? Well, you know that since they are all in millimeters, and you know how to do column addition, you can write, justify, and just add them up. 1,000,000 plus 1,000 is 1,001,000. When you add 11 to that, it's 1,001,011. But what does that really mean to you and me? 1,000,000 is too big a number to have much everyday recognition. And also, it is kind of silly to worry about 1 millimeter when we are dealing in kilometers. So that leads to two things that scientists and engineers must deal with. Significant figures, that's not including any more information in a number than what you can really justify or use, and estimates, the approximate values of things. You would not normally report the answer as 1,001,011 millimeters, but you might say a little over a kilometer. Maybe you'd say 1,001 meters. A few millimeters is just not significant, so why worry about it? And this takes us to the concept of the decimal point. We are very familiar with decimals from money and from our tax returns. Let's say you don't round off to the nearest dollar. Keep it in cents, but express it in dollars. Exactly $1 is 1.00. 10 cents or a tenth of a dollar, 0.10. 1 cent or 1/100th of a dollar is 0.01. The position of the decimal point identifies the unit we are using. Here it is, dollars. To the left of the decimal, the first column is dollars, the second column is tens of dollars, and the third column to the left represents hundreds of dollars. The first column to the right is tenths of a dollar, and the next column to the right is hundredths of a dollar. We could keep going and talking about thousands and even 10,000ths of a dollar, but these columns are just not significant. An example, the number 909.09 in dollar units is $909.09 of a dollar. So if you are dealing with dollars, but your calculator is giving you numbers to the far right, which would represent thousandths or 10,000ths of a dollar, those are clearly insignificant. So don't let people snow you with numbers that appear to be more accurate than they really are. Don't believe all of those numbers you see in your calculator, as many of them may be meaningless. And of course, if you make a mistake in entering a number into that calculator, the final result will also be meaningless. You know, the old rule is garbage in, garbage out. Numerical garbage, that is. We've dealt with distance, that's length measurements, and with money or currency. But now back to fundamental units. One of the fundamental units, together with length and time, is mass. You're used to it in pounds. In the metric system, it's kilograms. Bathroom scales measure in pounds up to several hundreds of pounds. Supermarket produce scales tend to measure in ounces to pounds. And your postal scale tends to measure in ounces and fractions of ounces. If you're a truck driver and you get on the scales on the interstate, there's no point in measuring in ounces or even in pounds because the trucks weigh thousands of pounds. So what is your weight in kilograms? What is a pound in kilograms or grams? Well, they're about 2.2 pounds in a kilogram, which makes about 454 grams in a pound. Let's say about 500 just to keep it simple. So a pound is roughly half a kilogram. Since there are 16 ounces in a pound, then there are 28 grams to the ounce. Let's say 30 to keep that simple. So 1 gram is about a 30th of an ounce. This box of prunes expresses it well. Net weight, 24 ounces. 1 pound, 8 ounces, 680 grams. Well done, Sunsweet. We've been using some abbreviations, some symbols, and we should define them. The first 4 you know, and the equal sign. The squiggly ones may be a little less familiar. They mean approximately equal and very roughly equal. And the final one refers to a precise definition. We'll meet them again. Mathematicians and accountants need to be very honest when they make an estimate or an approximation. So they use these squiggly symbols to make it clear what they mean. Although mass is a key fundamental measure, our personal laboratories, that's our kitchens, don't normally have devices to measure mass or weight. In the kitchen, you measure stuff by volume. In our English system of units, an ounce can refer to mass, that's 28 grams, and a different kind of ounce, a liquid ounce, refers to volume. This doesn't happen in the metric system. When we measure volume in the metric system, we use liters and milliliters. That's thousandths of a liter. A liter is roughly a quart. And you know that 1 quart is 32 ounces, liquid ounces. You're used to, hardwired, for our hodgepodge of English volume units. Gallons, quarts, pints, cups, tablespoons, even teaspoons. In the metric system, all you need are liters and milliliters. It's awesome. Let's do a little sensory calibration. Put a half-gram vitamin capsule on the end of your finger. Can you detect 500 milligrams? A half a gram? Sure. You can even detect 100 milligrams, about 1/300th of an ounce. Try this with your own vitamins and pills. There are all kinds of things in your cupboard, measured in both pounds or ounces and in grams. Become familiar with the differences in these two systems of units: English, pounds and ounces, and metric, kilograms and grams. To really become familiar, to have a gut feel for the units and numbers, you have to deal with them enough times that you develop new neural connections based on those experiences, just as you've already done with ounces, pounds, miles, and feet. Start looking at everything in terms of grams and kilograms, centimeters, meters, and kilometers, and milliliters and liters. When you buy gas, remember that there are roughly 4 liters to a gallon. Incidentally, gasoline in Europe isn't sold in gallons. It's sold in liters. It now costs about $1 a liter for gas in Europe. That would be about $4 a gallon here. That's one of the major reasons why most of us drive everywhere rather than take a bus. That's also one of the major reasons why there's so little public transit in most of the United States. Gasoline is so cheap that it's more convenient to drive a car. So the next time you fill up, just remember that if you were in Europe or Japan, you'd be paying 4 times as much. That's why Europeans and Japanese prefer cars with good mileage, whereas not everybody here in the United States is so inclined. Most of those 4x4s we love so much get only 12 to 15 miles per gallon. But those very little cars get up to 40 and some even more. It turns out that almost everything that we'll do in science, all of the quantities and all of the units we use, are based on distance in meters or centimeters, mass in kilograms or grams, time, usually in seconds, and in some cases temperature in degrees Celsius. We'll get to temperature more later. Everything else can be expressed in terms of those basic fundamental quantities. The bottom line, for now, 6 very important topics and skills: powers of 10, units, basic quantities, significant figures, decimals, and estimation. We've touched on a tiny part of the world of mathematics, the language of numbers and patterns. Measure, weigh, and time everything around you. Don't take your calculator too literally. Estimate whenever you can. And when you hear music, think math. Music and mathematics are closely connected. See you next time.
The beat goes on. The beat goes on. Drums keep pounding a rhythm to the brain. La-da-da-da-dee. La-da-da-da-da. Charleston was once the rage, History has turned the page, The miniskirts
thing.
Teeny bopper is our newborn king.
And the beat goes on. The beat goes on.
Drums keep pounding a rhythm to the brain. La-di-da-di-dee, la-di-da-di-da.
Grandmas sit in chairs and reminisce.
Boys keep chasing girls to get a kiss.
The cars keep a going faster all the time.
Mom still cries, hey buddy, have you got a dime?
And the beat goes on. The beat goes on.
Drums keep pounding a rhythm to the brain. La-di-da-di-dee, la-di-da-di-da.
And the beat goes on.